A molecule is so small we can't even see it. But if it were the size of a single grain of sand, 1 mole of sand would cover a city the size of Los Angeles 600 meters deep. So, the mole is a unit of measurement. It's a number, an inconceivably large number. It is determined experimentally and not by counting. Can you imagine that a computer counting 10 million atoms a second would take 2 billion years to count out 1 mole? The mole allows chemists to count molecules and atoms by weighing the mass of vast numbers of these particles. This is a mole of copper. This is a mole of water. And this is a mole of hydrogen gas. All have different masses, but each contains exactly the same number of particles. Trillions and trillions of them, but exactly the same number, Avogadro's number, 1 mole. The mass of a mole of any element is equal to the element's atomic mass expressed in grams. These are the relative atomic masses of the elements in the periodic table based on assigning carbon a mass of 12 units. Let's use the periodic table for some examples. Here's copper. Its relative atomic mass is 63.5. A mole of copper weighs 63.5 grams. Let's see another element. Here's magnesium. Its relative atomic mass is 24.305. A mole of magnesium weighs 24.305 grams. The same principle applies to compounds. Here's a water molecule, H2O. The relative atomic mass of oxygen is 15.999. The relative atomic mass of hydrogen is 1.008. If we add these atomic masses together, 1 mole of water will weigh 18.015 grams.
And so we see how we can go from the number of particles to the number of moles and then to the weight of a substance. Now we have some real live moles. Each of these substances is a mole: sugar, water, carbon, copper, and hydrogen. They all have different weights, but they all are made up of Avogadro's number of particles.